Okay, everybody, I'm going to teach you how to do solution stoichiometry, which is going to be combining solution stuff you just learned with the stoichiometry stuff we did a while back. In order to do this, you'll have to remember your formula. Molarity is equal to moles over total liters of volume. So you're going to have to remember that you are going to need to convert from milliliters to liters for everything. The first step you're going to want to do is write a balanced equation. So for this one, silver chromate will precipitate. That means that is going to be a product. So yield arrow, Ag2CrO4, it's a solid precipitate. So that's a product. There are two silvers because each silver is a positive one ion.
Teachers, I just remembered if you would like
and then CrO4 minus 2. You need 2 to balance that charge out to 0 for the neutral compound. When you add silver nitrate, AgNO3, it's a solution, so it's aqueous, to potassium chromate, K2CrO4, aqueous, because it too is a solution. And potassium is always a +1. Chromate, we already talked about being a -2, so it's K2CrO4. It's a double replacement reaction. So silver chromate is one of our products. Whatever we didn't use the first time is what we will have as our second product, which will be KNO3 potassium nitrate. This is soluble. And if you are unsure, you can check your solubility table. All nitrates are soluble, but we can double check, find potassium, find nitrate, boom, boom, soluble. So now that we have an equation, we need to balance it. We put a 2 here and a 2 there. We have our balanced equation. We are good to go. Second, calculate number of moles for each solution. In order to do that, we will rearrange that formula, which remember 3 is equal to 6 over 2. So if we're trying to find moles, we multiply these two. Moles is equal to the molarity times the number of liters. For both of our reactants, AgNO3, we have 250 milliliters, which means we have 0.250 for sig figs liters, and 0.750 molar. And we take that and put it in our calculator, and we're allowed to have 3 sig figs because there are 3 sig figs there. We will have 0.1875 from what our calculator says. Actually, don't worry about sig figs until the end. So this is fine. We have that many moles of AgNO3. For our other reactant, the potassium chromate, K2CrO4, we have 150 milliliters, which converting to liters is 0.1500 liters, and a molarity of 0.8000. We multiply those numbers, and that will give us 0.120 moles of K2CrO4 potassium chromate. From here, we will turn it into a stoichiometry issue. So, if we start with moles, up here, we need moles down here. And we will use our molar ratio of our balanced equation. So if we have moles of silver nitrate here, we need moles of silver nitrate here. Since we have a 2 here, we'll have 2 moles there. And then we will convert to what we are being asked about, which is the product of silver chromate So for every 2 moles of silver nitrate consumed, we produce 1 mole of silver chromate. 1 mole, 1 mole. And then the molar mass, silver chromate, you take 2 silver, which is 107.87, and then your chromium, 4 oxygen, and we end up with a molar mass of 331.74 grams of silver chromate per mole. And then you take your 0.1875 divided by 2, multiplied by 331.74. So you take that number, multiply by 1, changes nothing, divide by 2, multiply by 331.74, divided by 1, changes nothing. And for our silver nitrate, your theoretical yield with 3 sig figs is 31.1 grams of silver chromate. So if all of those moles get consumed in the reaction, we could theoretically produce 31.3 grams of silver chromate. Now we need to look and see what would happen if all of the potassium chromate gets consumed. So we have 0.120 moles of potassium chromate, 1 mole of potassium chromate consumed will produce 1 mole of silver chromate. Now we can copy off of our work earlier, assuming it's been done correctly. And if we take the 0.120, multiplied by 1 changes nothing, divided by 1 changes nothing, multiplied by 331.74, divided by 1 changes nothing. And if all of our potassium chromate gets consumed, we could theoretically produce, with 3 sig figs, 39.8 grams of silver chromate. And just like when we were doing limiting reagent stoichiometry, these two are theoretical yields. Since this one is bigger, it is a trash number. That is your real answer. That is one type of problem that you will have to do. If you are given information about 2 reactants, and you have a volume and a concentration, volume, concentration, and you are asked about a product, this is how you will do it. Third step, stoich, 2 grams of product. Okay, these are the longer questions that you'll have to do. A shorter version would be, let's see here, let's say how many milliliters of 0.30 molar barium nitrate are required to precipitate as barium sulfate by using all the sulfate ions from 30.0 milliliters of 0.400 molar aluminum sulfate. Okay, so first step again, balance equation. So we're having barium nitrate as one of our reactants. Barium, always a +2. Nitrate, always a -1. So we need 2 of those, aqueous solution. And we are using all the sulfate ions from aluminum sulfate. So that's another reactant. And aluminum, +3. Sulfate's a -2. So do the crisscross. Al2, SO4, parentheses, 3, AQ. Product will be barium sulfate, precipitate, solid, and then the other product will be aluminum nitrate, AlNO33, that's aqueous. Running out of room over there a little bit, but that's okay. So, now we need to balance it. So we put a 3 over here, a 1 here, a 3 there, and then a 2 over here. This one is shorter. We only have information about one of your reactants. And you have 30 milliliters, so in order to convert that, you just take 30 divided by 1,000, or you can move the decimal place over 3 times. So we have 0.03 liters, because, as we remember, moles is equal to molarity times liters. So we take that 0.03 liters, multiply it by our 0.400 molar, and that will give us 0.012 moles of our aluminum sulfate. So we have 0.012 moles of our aluminum sulfate, and right now we are being asked how much of the barium nitrate we would need to precipitate all those sulfate ions out as barium sulfate. So what we are going to do is we will start out with our 0.012 moles of aluminum sulfate. Then we're going to look at our molar ratio from our balanced equation. We have 1 mole aluminum sulfate, and we are going to see how much barium nitrate we need. So for every 1 mole of aluminum sulfate consumed, it requires 3 moles of barium nitrate. 1 mole aluminum sulfate gets consumed for every 3 moles of barium nitrate. Next up, we need to do a little bit of trickery. So we have a concentration of the barium nitrate, and right now it seems like we have a little bit of incomplete information. So you know that molarity is equal to moles over the liters, and if our concentration for the barium nitrate is 0.30 molar, and we're looking for how many moles there are, if we have 1 liter, X is equal to the concentration. So if we have 0.30 molar equals 0.30 moles over 1 liter, 0.30 divided by 1 is equal to 0.30. So using that as kind of a trick, we can just say that we have 0.30 moles of barium nitrate and 1 liter of barium nitrate. And then we can take our 0.012, multiply that by 3, divide by 1, changes nothing, multiply by 1, changes nothing, divide it again by 0.3, and that gives us 0.12 liters of barium nitrate. However, we are being asked about milliliters, and so we are going to have to multiply that by 1,000, or move the decimal place 3 spots. And so we're going to have 120 milliliters of barium nitrate as our answer. And since we have 2 sig figs here, 2 sig figs there, we're good to go for that one. So that is problem type number 2, and it's a little bit faster than the other one. And the only other type of question that you will have to do will involve a mass. So for some of these, you'll have to figure out and play around with it, work in a molar mass. So let's say, how many milliliters of 0.80 molar hydrochloric acid is required to consume 1.5 grams of sodium carbonate. And it produces carbonic acid. Again, step one, balanced equation. So we have hydrochloric acid, aqueous, plus sodium carbonate, Na2CO3, yielding carbonic acid, H2CO3. And if we use up the hydrogen, we use up the carbonate, we have NaCl left. Then we have to balance it, put a 2 here, put a 2 there. So our first step's done. We have a balanced equation. Now, we will start with our 1.5 grams of sodium carbonate. Find the molar mass of sodium carbonate. So 16 times 3 plus 12.01 plus 22.99 times 2 gives us 105.99 grams of sodium carbonate per 1 mole sodium carbonate. Molar ratio, 1 mole sodium carbonate reacts with 2 moles of hydrochloric acid to produce our products. And again, from here, we use that trick where if molarity is moles over liters and our molarity is 0.80, let's just say we have 0.80 moles and 1 liter of solution. And so we'll say 0.80 moles of HCl per 1 liter of HCl. So we take 1.5 multiplied by 1, which changes nothing, divided by 105.99 multiplied by 2, divided by 1, which changes nothing, multiplied by 1 changes nothing, divided by 0.80, and that gives us 0.8 with, let's see here, 2 sig figs, 0 liters of HCl. Never mind. 0.035, calculator error. That's in liters. We are asked for milliliters, so we are going to multiply that by 1,000, and we end up with 35 milliliters of HCl as our final answer with 2 sig figs. So sorry, calculator error. I don't think I pressed equal. So we end up with 0.035 liters, which converted to milliliters is 35. That's all you'll have to do for solution stoic. Play around with it. Email me if you have any questions.